Fine. Okay, so we're very pleased to have Harry Desmond from the University of Oxford, and he's going to tell us fifth force searches in galaxies.
All right, thanks very much. Thanks for the invitation to talk here. So I'm going to talk about a project that I've been working on for a few years now on searching for screened fifth forces in galaxies. So I'll start by motivating the galaxy scale as a particularly interesting one to search for new gravitational physics. And then I'll briefly introduce one of the most generic observational consequences of modified gravity, which is a fifth force. And then I'll describe the specific work that I've done on this. And that involves first mapping out the gravitational environments of the local universe to determine where screened or unscreened objects should be. And then using this to forward model two signals of chameleon or symmetron screened fifth forces, namely separation of stars and gas in galaxies and warping of stellar disks. And I'll describe how those come about. So this talk's based on these 5 papers here. Okay, so I don't suppose I need to justify modified gravity to you, but just to give you my own take before we get going. So traditionally, of course, we've wanted modified gravity to self-accelerate the universe's expansion as a route towards solving the cosmological constant problem. And that hasn't been working out too well lately, but it's not the only motivation. There's also the peculiarity of lambda CDM as a model built on GR, that to explain observations, we need a fine-tuned mix of components in the universe, most of which we don't really understand at all. But the main motivation for the kind of observational searches I'll describe is simply one of generality. There's no reason to expect gravity to be described solely by a single spin-2 field. And if you take the low energy limits of UV complete theories, then you tend to get a bunch of scalar, vector, and tensor gravitational degrees of freedom. Okay, so if we want to look for modified gravity, why should we consider looking in galaxies? Well, we've tested general relativity very precisely at small scales in the solar system and the lab, and also indirectly in cosmology. And you might think that that's good enough, that if we can show that general relativity holds in those 2 regimes, then it must be true everywhere. I think that's not right, and this plot tries to illustrate why. So each panel here shows the parameter space of gravity quantified by 2 of its fundamental variables, space-time curvature and Newtonian potential. The left panel shows where various types of object live in this parameter space. So we have compact objects, black holes and neutron stars at higher potential and curvature, planets in the solar system further down, and then cosmological systems, the CMB, large-scale structure and clusters at low curvature. The panel on the right shows observational tests in these different regimes. So gravitational waves and pulsar timing for compact objects, then PPN tests in the solar system, and then cosmological probes at the bottom. And you can see this obvious feature in the panel on the right, which is this huge gap in our tests of gravity that the authors of this paper call a curvature desert. And the only objects that really live in this gap are galaxies, which means that if there were a breakdown of GR at some threshold value of gravitational field strength, then it's quite possible for galaxies to be the only system in which this transition could be seen. And in fact, if we thought we understood gravity in the small scale regime, where we've been testing it for hundreds of years, but that modified gravity might be responsible for cosmological phenomena, then this intermediate galaxy scale is possibly exactly where we'd expect modified gravity to kick in. Okay, so now what kind of behavior would we expect deviations from GR to give in galaxies, and how would we search for them? So almost any modification you make to the Einstein-Hilbert action introduces new dynamical degrees of freedom. And these naturally couple to the Ricci scalar and hence introduce new types of interaction between particles, which are called fifth forces. And these can take a number of different forms, depending on the property of the field that mediates them. So here, for example, is the modification to the gravitational potential due to a new light scalar field. So you can see that the normal Newtonian force is modified with a Yukawa term, with a range given by the mass of the field, and a strength, which I've parameterized here relative to gravity as delta G over G Newton, which depends on the coupling coefficient of the field to mass. This violates the inverse square law, which means that it's strongly constrained by local tests of gravity, torsion balance and atom interferometry type experiments in the lab, and then astrometric experiments in the solar system. And in particular, the constraint on the ppn parameter gamma from the Cassini mission is so strong that it means that if this fifth force is universally coupled, then either it has to have a strength much less than gravity, or it has to have a range that's much smaller than the solar system. And if either of those things is true, then it's not going to have any significant effect in astrophysics or cosmology. But that's not the end of the story, because we've realized in the past couple of decades that there are broad classes of Lagrangian that cause the new field to become nonlinear in high density regions in a way that suppresses the fifth force. And this is called screening. Now, just a few basic types of screening. So in the chameleon mechanism, the mass of the field becomes high at high density, so the range of the fifth force becomes short. In camouflage, the kinetic term becomes nonlinear, which decouples the field. And in symmetron and Weinstein, the coupling coefficient of the force to matter effectively goes to 0 in high density regions. And the fact that the whole zoo of modified gravity models has to implement one of these few mechanisms to be observationally viable means that tests of specific screening mechanisms are much more general than tests of specific modified gravity theories. Okay, so now we're getting on to the new part, which is how to actually search for screened fifth forces in astrophysics. So the logic of screening implies roughly that general relativity should be recovered in strong field regions, for example, within dense galaxies like the Milky Way, while a fifth force should be present in weaker field regions like dwarf galaxies and voids. And the different ways in which models screen imply different properties of the field as being the pertinent one for setting the degree of screening, and hence which observational proxy is the relevant one for determining whether a given object in the real universe is screened or not. And the approximate mapping between screening mechanism and observational proxy is shown here. So very roughly, in the chameleon mechanism, it's the potential that develops nonlinearities when screening kicks in, which means screening effectively occurs at a threshold value of the scalar field. The scalar field obeys the same Poisson equation as the Newtonian potential, just maybe with a mass term, which means that the two are sourced by surrounding mass in the same way. So a threshold value of the scalar field roughly corresponds to a threshold value of Newtonian potential. And similarly, in camouflage, it's the kinetic term that causes screening, which is a first derivative of the scalar field, and therefore maps onto a first derivative of the potential, which is acceleration. And Weinstein is a second derivative, which maps onto curvature. So in case that's a bit too hand-wavy for you, here's some more concrete justification for this mapping in the case of chameleon screening, which is the one I'll mainly focus on. So this is a cosmological n-body simulation in f of r gravity, which screens by chameleon. Each of the points in this plot are halos produced in the simulation, and they're color-coded according to how screened they are, with red being unscreened and blue and black being screened. And they're plotted in the parameter space of the mass of the halo itself on the x-axis and the Newtonian potential sourced by other mass within one Compton wavelength of that halo on the y-axis. And you can see that it's possible to accurately pick out unscreened halos by requiring both that they have low mass, so they don't screen themselves, and that they live in low density regions, with low external potentials so that they're not environmentally screened. Okay, so given that, the way to search for a screened fifth force in the universe is pretty clear. We need to map out these quantities over the local universe to determine which galaxies we'd expect to be screened or unscreened in a given theory. And then we need to devise observables for a fifth force in the unscreened galaxies. And if we can forward model those observables as a function of the fifth force properties, then we can constrain those properties in the normal Bayesian way. And so that's the goal for this talk. And I'll describe these steps in turn. So in principle, measuring the gravitational field strength at any point in space is easy. You just sum up the contributions from all the surrounding mass. But in practice, it's rather hard because most of the mass is dark matter and we don't know where it is. So my starting point for modeling this is to take a magnitude limited galaxy survey, either 2M++ or SDSS, and use a model for the galaxy halo connection to associate a dark matter halo with each of those galaxies. And then I'll fill in lower mass halos by calibrating with an n-body simulation. So the idea there is to identify regions of the simulation that look similar to a given region of the real universe in terms of massive halos, and assume that those two regions have the same or similar amounts of smaller substructure as well. And finally, there's mass in longer wavelength modes of the density field that isn't captured by the halo model. And to add that requires cosmological structure formation models that are constrained to match the local large-scale structure. And for that, I use the results of the Borg algorithm, which I can explain later if people are interested. Okay, so combining those various components gives results that look like this. So these are slices through the potential, acceleration, and curvature fields out to 150 megaparsec, with the Milky Way at the center of the box. And the panels on the bottom are the distributions of those variables over the galaxies in the 2M++ survey, with some window function that sets the radius within which sources are considered to contribute. That's the 10 or 3 megaparsec in the legend. So this tells us the regions we would expect a fifth force to be active in, given screening. So for example, under a chameleon or symmetron model, it's the regions of shallow potential, which are these blue regions in the upper right plot, that we would expect to harbor unscreened galaxies. Okay, so now let me say a bit more about how this plays out in a specific modified gravity model, which is the Hu-Sawicki model of f of r. So if you specify n in this theory, then it has a single free parameter called fr0, which is the background, the cosmological background value of the scalar field. And that determines both the Compton wavelength of the field, which is the range of the fifth force, and also the threshold value of Newtonian potential at which screening kicks in, which is sometimes called the self-screening parameter, chi. So for example, for fr0 of 10 to the minus 6, we have a Compton wavelength of 3 megaparsec and a threshold potential of 1.5 by 10 to the minus 6. The Compton wavelength is the distance over which the fifth force operates. So if we sum up the potential due to all sources within that distance, then we find that galaxies in this part of the distribution are unscreened towards lower potential, and on the right-hand side of the red line, galaxies are screened. And similarly for any other value of fr0. Okay, so now that we've got a handle on which galaxies are screened versus unscreened, we need to know what we can expect to see in unscreened galaxies. And I'll describe two signals, both of which are due to the same basic effect. So if the galaxy as a whole is unscreened, then the gas and dark matter in it interact with surrounding mass via a fifth force. But main sequence stars, on the other hand, are often sufficiently massive that they self-screen due to their own deep gravitational potential wells, which means they'd feel just regular gravity. So the Newtonian potential at the surface of the Sun is around 10 to the minus 6, while dwarf galaxies in voids can have potentials a bit lower than 10 to the minus 8. So there's a sizable range of FR0 or chi values for which the stars are screened, but the gas and dark matter aren't. And what that means is that if the galaxy is falling in an external fifth force field, the centers of the dark matter halo and the gas move ahead of the center of the stellar disk in that direction. And that goes on until an equilibrium is reached, where the extra force on the stellar disk, due to its offset from the halo's center, exactly compensates for the fact that it doesn't feel the fifth force. So both components have the same total acceleration. And that's described by this equation. So R star is what I'll use to denote the offset between the center of mass of the stars and gas. The left-hand side is the restoring force on the stellar disk due to the halo. And the right-hand side is the fifth force pull on the gas and dark matter. So the second signal is essentially a generalization of the first one across the stellar disk by requiring that all parts of the disk feel the same total acceleration. And given the displacement between the center of the disk and the halo, that requires the disk to warp into this characteristic U shape that's described by this equation that you can derive quite straightforwardly. And for the purpose of doing an inference with this, I'll summarize the warp curve with a single summary statistic that describes the overall magnitude of a U-shaped warp, essentially by integrating the deviation from planarity across the major axis of the disk. Okay, so
Harry,
now that we have some idea of...
Harry, can I ask what assumptions you're making on the density of dark matter here? Are there any assumptions going in there?
Oh, good. So in this equation here, there are no assumptions. So this would just be the total enclosed mass of dark matter within some radius. So that can have any density profile. Very shortly, when I come to actually modeling this, I'll impose some more assumptions to get some concrete numbers out.
Thanks.
Okay, so first off, let's collect some observational data for these two effects. So to measure gas star offsets, I'll cross-correlate the alfalfa catalog of H1 sources with the NASA Sloan Atlas, which is optical and near-infrared photometry, mainly from SDSS. So H1 traces neutral gas, and the optical photometry traces starlight. So that gives an observed value of R star for each galaxy in this sample projected onto the plane of the sky. For warps, I'll use images of edge-on disk galaxies in the NSA. I'll cut both samples at 250 megaparsec, which leaves about 16,000 galaxies for the offsets, and about 4,000 for the warps after you've selected only edge-on disks. And you can see down here that the angular separation of the stars and gas is about 20 arcseconds on average, which is dominated by the angular resolution of the H1 beam. And the magnitude of disk warping is about 0.1%. So these plots just give a bit more information on calculating the warp statistic. So these are the raw R-band images of two example galaxies in the NASA Sloan Atlas. If you rotate them so that the major axis is along X, and then measure the intensity-weighted mean position of Z, the perpendicular direction on the plane of the sky, in each X pixel, then you get these warp curves. And these are what go into this formula here to calculate the warp statistic, W1. Okay, so now we need to build a likelihood model for the data given a fifth force, which means solving these equations that we had back here. These two for warps and this one for gas star offsets. And this is where we need to make more assumptions. So the predicted values of those signals are a function of three things. The properties of the fifth force, which we're trying to infer, The gravitational environment of the galaxies, which determines whether they're screened or not, and also the magnitude of the external fifth force field. And then finally, the internal structures of the halos that host those galaxies, which set the restoring force on the stellar disk. So the gravitational environment comes from the gravitational maps that I described earlier. To model the host halos, I'll assume a power law density profile of dark matter across the galaxy with a normalization that's connected to the luminosity of the galaxy through a model called halo abundance matching. And if you plug this into the formulae that I showed earlier, then you derive explicit equations for the two signals that we're interested in as a function of these parameters. And this plot here shows the expected warp curve for different values of beta, this power law exponent in the dark matter density profile, for representative or typical values of the other parameters. So beta equals 1 here would correspond to an NFW profile within the central region of the halo. But observationally, the central regions tend to be more chord, which means you could have a lower beta. So I'll take a fiducial value of 0.5 when I actually do the inference, but I've checked explicitly that varying that between 0 and 1.5 doesn't affect the results much. Okay, now to do a Bayesian inference, we need more than just point estimates for R star and W1. We need full probability distributions in order to model the uncertainties. And I'll get them by Monte Carlo sampling the uncertainties in the gravitational maps and the galaxy halo connection terms that go into these equations to build up galaxy by galaxy distributions of R star and W1 values that describe the likelihood for a given galaxy. So these discrete likelihoods are shown by the blue histograms here for two example galaxies. And to convert them into a continuous likelihood function to use in Bayes' theorem, I'll fit Gaussian mixture models to them, which are shown by these curves. And if you do that, then the likelihood for some signal value y, where y is either one component of the gas star offset on the sky or the magnitude of the warp, as a function of the strength of the fifth force, delta G over G, and the range, lambda C, is given by a component in case the galaxy is screened, which is the first term, in which case the predicted signal is 0. And in case the galaxy is unscreened, a sum of ng Gaussians, which are these Gaussians fitted to the likelihood, with weight W, standard deviation S, and mean Y bar. And Fi, which is the number that weights these two terms, is the unscreened fraction for galaxy I, which is the fraction of Monte Carlo realizations of the model in which the galaxy's total Newtonian potential is less than the threshold value for screening in the Hu-Sawicki model, so that the galaxy is unscreened. Okay, so here are some first results. So the top left panel here shows the predicted gas star offset for all 16,000 alfalfa across SDSS galaxies. This is the modal offset, so essentially the peak of this distribution, plotted against the Newtonian potential of the galaxy. And the top right is the analogous plot, but for the observational data. And then the panels on the bottom show the same things, but for the warp statistic instead. So you can see that in the predicted case, there's a strong correlation between the values of the signals and the Newtonian potential that the galaxy lives in. That's just because the signals increase with the strength of the external fifth force field, which is sourced by the same surrounding mass as the potential. So a larger value of potential means more mass, which means a larger fifth force field. So you predict stronger effects. But of course, that's only true up to the screening threshold, which is shown by the vertical dashed lines, because beyond that, the galaxy is screened, so the predicted signal goes to 0. And that's why the red points are cut off. The blue and green points don't include screening, so they essentially just carry on to higher potentials. And you can also see that, at least in the case of the gas star offset signal, the observed values are significantly larger than the predicted values, even in this relatively strong fifth force model, where the fifth force is as strong as gravity. So the observed offsets are about 10 up to, well, I mean, around 10 kiloparsec on the plane of the sky. And the predicted ones are around 1 kiloparsec on average. And what this means is that at most a small part of the signal can come from a fifth force. Most of it has to be noise. But the likelihood that we had here didn't have any provision for noise, because it assumed that if the galaxy was screened, or delta G over G was 0, then there would be no effect. There would be no separation of stars and gas and no warping of stellar disks at all. So we need to now build some noise into this model before we use it to derive constraints on the fifth force parameters. So the noise has two possible sources. The first is simply a measurement uncertainty. So for example, the H1 measurement of the gas involves 21 centimeter radio observations, which have fairly poor spatial resolution. And the other source of noise is physics unrelated to a fifth force, but that also moves stars and gas around differently or warps galaxies. So for example, ram pressure affects gas but not stars, or stellar feedback could couple differently to baryons in different phases. Now, ideally, we would have explicit models for those effects that we could combine with the fifth force model to derive a total likelihood. But unfortunately, we don't, which means the best we can do is to parameterize them in some way and then marginalize over them in deriving the fifth force posteriors. So I'm assuming here that the noise is Gaussian, which means that the fifth force likelihood for galaxy I that I showed earlier is convolved with a Gaussian of width sigma I, and that's what this equation shows. But I can't marginalize over 1 degree of freedom per galaxy. That's too many. So I need to impose some relation between the sigma I values. And there are 3 basic possibilities for that. So the width of the noise distribution could be the same for all galaxies. It could be proportional to the distance to the galaxy, which would describe fixed angular resolution, or it could be some more complex function of galaxy parameters. And for the sake of simplicity, I'll focus on the first 2. So specifically what I'll do is, for each of the 2 data sets, the gas star offsets and warps, I'll fit 3 noise models, one with just the first term, one with just the second term, and one that includes both terms. And then I'll pick the model that minimizes the Bayesian information criterion of the fit as a measure of goodness of fit relative to the number of degrees of freedom. And that selects the constant term for the noise for the case of warps and the distance dependent term for the case of gas star offsets.
So, Harry, do you understand why that is the result? And could you have guessed this from the beginning? There would be warps and offsets?
Partially. So for the offsets, I do understand it. That's because the noise is dominated by the angular resolution of the H1 beam, which is about 20 arc seconds. So it makes sense then that the physical resolution should be proportional to distance, because the further out you go, a fixed angular resolution means a larger physical distance. For the warp case, it's not so obvious. I mean, I think this, and I couldn't have guessed in that case, but I think, this just shows that the noise is probably set by something intrinsic to the galaxy rather than by a measurement uncertainty that will increase with distance. So it's more this astrophysical contribution that I mentioned earlier rather than the measurement noise which dominates for the gas star offsets. But really, this is just an empirical result. I don't have particular insight into why the value for the noise should be as it is for warps. Okay, so now finally we can plug this likelihood and the data into a Markov chain Monte Carlo algorithm and actually derive some constraints on the free parameters. So this plot fixes the fifth force range to 0.4 megaparsec and looks at the constraints on the strength of the fifth force, delta G over G, and the two noise terms. So you can see that the noise parameters are well constrained and they're not degenerate with delta G over G. And that's just because the noise is set by the overall widths of the observed signal distributions, while delta G over G is constrained by the residual correlations of the signals with the gravitational environment and halo properties of the galaxies, according to the fifth force model. And those are two largely orthogonal pieces of information. So this plot shows more generally the fifth force constraints as a function of lambda c between 0.3 and 8 megaparsec, which is roughly FR0 in the Hu-Sawicki model between 10 to the minus 8 and 10 to the minus 5. So the constraints strengthen as you go to larger lambda c because more galaxies become unscreened and the fifth force field becomes stronger because the fifth force has a larger range. It turns out that the warp inference is more constraining at small lambda c, while the gas star offset inference is stronger at larger lambda c. And the constraint on FR0 specifically comes from setting delta G over G to a third, which requires FR0 less than 1.4 by 10 to the minus 8 at 1 sigma. And with FR0 that low, practically no object in the universe is unscreened, which means FR0 can't really have F of R, sorry, can't really have any relevance to astrophysics or cosmology. Okay, then the final plot here shows the results for a few variations around the fiducial model. So the black line is the same joint constraint that I just showed. The red and blue lines are the constraints with screening switched off, so that all test galaxies are unscreened and all masses source a fifth force field, not only the unscreened ones. So that gives stronger constraints. And one particularly interesting application here is to models in which the fifth force operates only in the dark sector. So the warp inference is sensitive to that because it probes the difference in fifth force coupling to the dark matter in the halo versus the stars in the stellar disk. And that sets a constraint of delta G over G around 10 to the minus 4. So the gas star offset, no screening constraint, which is the blue line at the bottom, would apply for the case in which the fifth force couples intrinsically differently to stars and gas, which seems like more of a contrived model. And then the dashed lines here show the results of varying the relation between lambda c and the cell screening parameter chi by 1 order of magnitude around the n=1 Hu-Sawicki relation. So if you increase chi, more things become unscreened, so the constraints tighten. And if you reduce it, more things become screened. So by varying this chi lambda c relation, you can use these results to constrain Hu-Sawicki with a different value of n, or any other chameleon or symmetron model, which would just have some different relation between the range of the field and the point at which screening kicks in. So that's it for the results. But now I want to spend a few minutes talking about some of the systematics that this test could be sensitive to. So the most significant one is that the noise model might be overly simplistic. So I've assumed that any apparent signal produced by non-fifth force physics is Gaussian and correlated between galaxies in a very simple way. And that's not going to be true in detail because baryonic physics, like Ram pressure and stellar feedback, will depend to some extent on galaxy properties and environment. But the question is whether that makes it significantly degenerate with the fifth force. So to get a handle on that, I've been looking at warps and gas star offsets in cosmological hydrodynamical simulations, which have a full galaxy formation model built in. So the plot on the left here shows the distribution of one component of the gas star offset across the galaxies produced in the Horizon-AGN simulation. And the plot on the right shows the correlation between the offset produced in the simulation and the stellar mass of the galaxy. So the offset is well described by a Gaussian random noise at the spatial resolution of the simulation, which is about 1 kiloparsec. And it seems that it doesn't correlate significantly with galaxy properties like mass. So that's good news for the noise model that I used, in which it didn't correlate with anything. But this is work in progress to validate that noise model more thoroughly using simulations. So the second systematic, potential systematic, is that I assumed various things from lambda CDM when I modeled the density profiles of the halos and the large-scale gravitational field. But really, this should be done self-consistently in modified gravity. So I think this is fine because the difference should be very small for a fifth force as weak as the constraints imply. So for example, F of R simulations typically need FR naught around 10 to the minus 6 or greater to produce noticeable differences to lambda CDM. But here we're talking about field values 2 orders of magnitude smaller. And finally, the amount of dark matter in the very central regions of the halos, which sets the restoring force, is quite uncertain. So I've tried a few different models for that, including varying the beta parameter as I described earlier, and the results don't change very much. But it would still be useful in the future to repeat this kind of analysis on a sample of galaxies that have more detailed dynamical measurements in the central regions to avoid having to make some of these assumptions about the form of the halo density profile. Okay, so that's pretty much it. Hopefully I've convinced you that galaxy morphology contains a lot of interesting information about fundamental gravitational physics, and that statistical inference over the full galaxy population is a good way to extract it. So I've shown how to map the gravitational variables that determine a screened fifth force over the local universe, and then applied that to 2 specific tests of chameleon or symmetron models. So the constraints imply generally to a fifth force on astrophysical scales, but 2 case studies that are maybe of particular interest are to the Hu-Sawicki model of F of R, where you get this very tight constraint on FR naught, and to an unscreened force that acts only in the dark sector, for example, in some coupled quintessence type model. And the future is bright, so there's more signals still to explore, and the massive galaxy surveys that are currently running or that are planned for the next few years will provide lots of data to search for them. And that's it. Thanks.
Thank you very much. Okay, any questions or comments? Been a bit. Anybody online? Stephen, you have something, yeah? Stephen has something, please.
Hello, Harry.
Hi.
Hi. Yeah, thank you. Very interesting talk. So I had a couple of questions. There's also Einstein's.
Yes.
Okay, but it's not density dependent. So how does that feed in?
Oh, sorry. There is also Weinstein screening. These tests don't apply to Weinstein screening.
Oh, they don't apply to Weinstein.
No, sorry. I think I missed a part of your question there. They don't apply to Weinstein screening. You need different types of test for that. So Weinstein screening also breaks the equivalence principle in galaxies, so produces interesting signals, but it does it in different ways, as you pointed out. So one of the interesting ways of testing that, which I've also written about recently, is to look for differences in behavior between stars and black holes in galaxies. So, for example, in Galilean models, which are sort of archetypal Weinstein screened model, Galilean doesn't couple to the black hole because it satisfies a no-hair theorem, but it does couple to stars, which means you get similar sort of effects in terms of offsets developing between different components of galaxies, except in the case of Galileans, it's between the central supermassive black hole of a galaxy and the stellar disk, rather than here where it's between the gas and the stellar disk.
Thanks.
Does that answer your question?
Great, thanks. So another question. So these days there's gravity models. I think dynamics now as well. So
sorry, I missed another word there. You're a bit crackly.
Yeah, I'll use it. Hang on. Hello, can you hear me?
Yeah, that's good.
Okay, so you have these days there's I think with hydrodynamic. So can you use those and test the model dependence and see if you that you are.
Sorry, I'm still missing words, but I think you're asking hydrodynamical simulations in F of R.
Yes.
Yes. Good. So yeah, they exist now, which is very nice. They're quite expensive to do, and there are only a few groups doing them, which is why I would rather make my tests independent of them if possible. And one of the nice reasons why that's possible is that the groups that have been doing those simulations have shown that the effects of baryonic physics and modified gravity are largely decoupled from one another. So there isn't a complex interplay between baryonic physics and modified gravity. If you just include some correction to whatever observable you're interested in due to modified gravity and then multiply that onto the one due to baryonic physics, then you get a pretty good approximation to the total result. So that's one point. And then the other point is, as I was mentioning about doing this self-consistently in modified gravity, you only get significant effects, at least on any kind of cosmological observable, when you have fairly large values of FR0. So I think it's safe to assume lambda CDM as a background for those parts of the analysis when FR0 is below 10 to the minus 6 or 10 to the minus 7. And then, focus solely on the smaller scale physics using this kind of model that will be independent of power spectra, clustering, and so on, that are what the simulations in F of R are really gunning for.
Okay, thank you.
There a question online? If not, let me see. Yeah, okay. Harry, I just said about how these things were being received in Nottingham.
Nottingham?
Yeah, this is modified gravity in the UK.
Oh, you think so? I don't know. I think there are a few centers.
So you get invited to give talks, do you?
Yeah. No, I know the people at Nottingham very well, actually. Claire Burridge and Ed Copeland.
Also working on stuff.
Okay, yeah, no, so Claire especially has been very enthusiastic about this kind of work from the beginning.
Yeah, it looks pretty powerful.
Yeah.
Yeah, I think by basically combining your results with some other stuff that we have done, one can probably say that some of these swampland conjectures of Kumran-Vafa and string theory are probably not realized in the real world.
Yeah, exactly. So the way I, relate that to this is in terms of essentially a model that has a fifth force only in the dark sector.
Yeah, exactly.
That's effectively what happens in those models.
And
as I mentioned, the warp inference is sensitive to that. And I think if you had a fifth force 10% of gravity or order 1, it would be pretty obvious in terms of the structures of galaxies. And you would fairly clearly see a correlation between their structures and the fifth force field as I've modeled it, assuming I haven't done something crazy.
Yeah, I guess in some sense you could take Kumran's model, where I think he has a coupling, like an exponential coupling, where it's 0.3, and if you run it in the other end, you could probably see that it's very drastic.
Yeah, I think that's right. And that is also something I've done. I mean, generating mock data according to some fifth force model and making sure that you can rule out models as extreme as, or, you know, as small as I've claimed to rule out. And that does check out. So I think you could definitely do that and show that explicitly.
Okay, well, thank you very much for a very interesting talk. It's good to see these constraints. I'm sure it's going to basically influence where the field is going in the future.
Well, hopefully, I hope.
Metal, in some sense. Okay, well, thank you very much for the talk.
All right, yeah, thanks very much for inviting me.
Yeah.